Okay, let's go for the next topic. It's gonna be angular momentum. That's the symbol for angular momentum. Imagine that we have a particle moving at this instant, right, with some velocity, and this is relative to an observer, an origin at that position. Let's call it this the vector position. Now we can relate this to a net force. Right, the net force is found to be related to the change in the angular momentum, correct? So the net force is defined as the derivative of momentum with respect to time, and momentum, the linear momentum, we know is defined as the product mass times velocity, in this case with respect to time. Okay, because we're dealing with rotational motion, and also force is related to torque, the tau, the symbol is tau, remember? So we relate then this force in this way. This is the torque is defined, remember, as the cross product of R, the lever arm, or the vector position, times the cross product R and a force. And this is equals to, when we substitute this value, right, R cos the derivative of linear momentum respect to time. Correct? Because we're involving the derivative of momentum respect to time, we can go back, right, and try to find the derivative of this product, cross product, okay, respect to time. And this is equals to the derivative of this one with respect to time cross the linear momentum, correct, plus the position vector cross the derivative of this linear momentum. Okay, but what is this? This is just velocity cross mv plus r cross, right, the derivative of this linear momentum respect to time. But v cross v is 0, correct? That's 0. Means that the derivative of this cross product is just equals to this part. But this part is coming from here, and this is equals to torque, tau. Conclusion, the torque can be also represented as the derivative of this quantity, R cos mv with respect to time. Correct? This is a vector notation. When we compare this one more times to force, the net force, okay, this is the net force equals to the derivative of linear momentum with respect to time, correct? We can see that this quantity is related to momentum, and we call this the angular momentum, right? So the angular momentum is defined as the cross product of R and the linear momentum. Also, correct, we can represent in this way. It's going to be R and V sine theta, correct, in this direction. What should be the direction of the angular momentum? Remember, every time we have cross product, to find the direction of the quantity, we use the right hand rule, correct? Right, like in this case, minus the force, so we have that this is going to be the direction of the angular momentum using the right hand rule. Perfect. So also, when we substitute this value right here, what do we have? We found that torque is equals to the derivative of this angular momentum with respect to time. Perfect. Now let's see what happens if we have a particle. If we have a particle that moves in circular path, right? We have a particle that moves in circular path at this instance, right? That's the momentum. This is the mass. This is the distance r, correct? And we're looking for the angular momentum. Okay, how do we define angular momentum? Angular momentum is, let's try to find the magnitude first, correct? is equals to r mv sine theta, according to this equation right here, only the magnitude first. Okay, perfect. And then it's equals to rm, but what is v? V, because now we are in rotational conditions, let's try to find the relationship of this v and rotational quantities. We know that v, tangential velocity, is equals to r times omega. Okay, perfect. So it's gonna be r times omega. And the angle right here is the angle between r and v. In this case, v is related, right, to momentum and is perpendicular to r. So it means that the angle is 90 degrees. Sine 90 is 1. Perfect. So this equals to r squared omega. We found before that moment of inertia for one particle moving in circular path, right, is equals to mr squared. So this is equals to moment of inertia times omega. Correct? So this is gonna be then the magnitude for linear for angular momentum equals to moment of inertia times omega. We know from the previous chapters that when we have a particle moving in circular path and we're looking for omega, right, we found, again, we use the right hand rule, and we found that in this particular case, it's going to be the direction of the angular velocity. Because these are related, right, this is the magnitude, we can call this the vector notation. So you can see they have the same direction. So we can take this also as a direction for the angular momentum, correct? Going up in this figure. Perfect. This is one particle. What happens if we have a solid? Okay, let's go for a solid. A disk. For simplicity, one more time. This is the axis of rotation. This is the path of a particle. This is m sub I, and this is b sub I. And this is the radius r sub I. Correct? Now, what should be the angular momentum for this particle? Right? Again, imagine that this is z direction. This is the particle moves in xy plane. So the perpendicular one is gonna be z direction. Perfect. According to this definition, it's gonna be equals to r sub I, m sub I, b sub I, right, sine theta. But one more time, the angle between r and v is 90 degrees, so sine 90 is 1. And then this is equals to, also let's substitute the values of v as we did before, right? It's gonna be r sub I, m sub I, what else? It's gonna be r sub I times omega. Correct? And this is again m sub I, right? R sub I squared times omega. Now let's find the angular momentum, the torque angular momentum in the z direction. So it's equals to the sum, right, of all these particles, correct? And it's equals to the sum of m sub I, r sub I squared times omega. Then one more time, we define this as moment of inertia for all the particles. It's gonna be moment of inertia times omega. So the angular momentum, right, when we're dealing with a solid, right, in this case, is equals to the moment of inertia in z direction is equals to, angular momentum. The angular momentum in the z direction is equals to moment of inertia times omega. Angular momentum, moment of inertia, moment of inertia. Correct? Perfect. Now let's go to the case when we have a particle moving in a straight line. One more time. If we have a particle moving in a straight line, imagine this is the case. Let me do it. Right here. This is the path. At the beginning, the particle is right here with some momentum, correct? Some momentum, and later is right here, right? Momentum is conserved. And this is an observer, the origin, correct? If we are right here, right, this observer origin sees that actually this particle has, right, even though it has a linear momentum from this particle, we can see it also has, right, angular momentum, because we have covering an angle, right? Angular momentum. And let's call this distance R. Well, this is gonna be RA. Imagine this is point A. It's gonna be R sub A. And this is point B. Later is right there, right? It's gonna be R sub B. This is origin right here. Perfect. And one more time, imagine this is the angle between R and B is equals to theta B. Correct. And right here, this is the angle, right? Theta A. Correct. Now, because these angles are the same, theta B, we can call this again the perpendicular distance to this path. Okay, great. Now let's pay attention on this part. This is the angles, let's call it theta 1, but we know that when we have this angle similar to this one, this is again 120 degrees and this is 60 degrees. We know that sine 120 is equals to sine 60 degrees. Now we call this represent theta A and this represent theta 1. So we can see from here, correct, that sine theta A is equals to sine theta 1. Perfect. Now let's relate these angles to the perpendicular R. Let's do it. So perpendicular R is equals to what? Is equals to RB sine theta B, correct? And also is equals to, using this angle, these two angles, the sine of these two angles are the same using this condition, is equals to RA sine theta A. Correct? Because look at this position, what do we have? We have that the angular momentum at A is equals to RAP sine theta A. Correct? And right here, the angular momentum at B is equals to RV momentum, right? Sine theta B. But when we use this condition, right, we can see that angular momentum at A is equals to angular momentum at B. It is equals to R perpendicular times P. Correct? Means what? That the angular momentum is constant. Correct? When the linear momentum, even though it's in a straight line, correct? We can also relate it to an angular momentum, and the angular momentum is constant. How we can get a constant angular momentum? Well, this in the same way we did for linear angular momentum. Correct? For linear case, remember we use force. Force is equals to the change in momentum, right, with respect to time. This is the external force. If this external force is 0, right, if force is equals to 0, then what do we have? Then 0 is equals to change in momentum with respect to time. Correct? But also from here we have that 0 is equals to change in momentum. Means what? Means that final momentum is equals to initial momentum. Conclusion, momentum is conserved. Linear momentum is conserved. When the external force is 0. This simply happens for angular momentum. Let's apply the same steps. We have torque is equals to, according to this equation, changing angular momentum with respect to time. If torque, right, the external torque is 0, then we have that 0 is equal to change in angular momentum with respect to time. Perfect. From here we can go to the conclusion, the same thing as right here, correct? That angular momentum at the end is equals to angular momentum at the beginning. Again, in this case, angular momentum is conserved. The same thing as linear momentum. And that's why it's very important, this quantity, right? Because the quantity is conserved when we have interaction. The total momentum, remember, the torque momentum after the collisions or interaction is equals to the torque momentum right before the interactions. The same thing happens right here when we're dealing with angular momentum. Great. Now let's go to one example. Let's apply angular momentum and let's apply these formulas and see how we can use again angular momentum to solve problems. Let's compare the angular momentum to a case we were dealing just with forces. Imagine that we have this example. We have this object. We have it's connected by a rope right to another object right here. This is a pulley. It has moment of inertia, also has a mass. Imagine that this is M1. Imagine this is M1, this is M2, and let's call this M3. Correct? Imagine that the rope is always making contact and doesn't slip on the pulley. When that happens, we can see that the velocity, right, the velocity of the pulley is equals to R times omega. Correct? Now let's see what happens when we're dealing with translational motion and the rotational motion. Let's go to translational motion. Let's see what happens. Well, in this case, let's find the forces acting on this mass M1. To do that, remember we use the free body diagram. Forces acting is gonna be tension. Let's call this tension 1, and let's call this tension 2. It's gonna be tension 1. Also remember we have, in this case we have no friction to simplify the calculations. It's gonna be M1G, and this is the normal for mass 1. So the next step again is find the net force. In this case we have only tension, so tension 1 is equals to M1 times the acceleration. Correct? Perfect. Also remember, we mentioned before when we were dealing with torque, correct? If the motion goes counterclockwise, the direction is positive, and clockwise is negative. This is when we have only one object. But when we have a system like this one, we take the direction of motion to be the positive direction. In this case, the direction of motion goes in this way, right? The acceleration goes in that way. So this direction is positive now, correct? In this case, should be negative when we take, if we take only the pulley by itself. But when it's part of a system, we have to take right this direction of the pulley in the direction, the positive direction of the pulley in the direction of motion. In this case, this is the direction of motion. Perfect. Now let's go to the next object. The next object, because we're in translational motion, so then it'll be M2, right? M2. What happens to M2? Well, the same thing. We have the free body diagram. Correct, forces acting gonna be M2G. What else? Tension 2. So what is the formula that for this case? Well, we have that M2G minus T2 is equals to M2 times acceleration. Correct? Perfect. Now let's go to rotational case. Rotational. In this case, we have, correct, the pulley. That's the pulley. This is radius R. We have this tension 1, and this is tension 2. Remember, this is the direction of motion. In this case, acceleration. Okay. So let's use torque. What should be the net torque? The net torque is equals to T2 times R. What else? Minus T1 times R. Correct. Is equals to in the previous chapter we found that torque tau is equals to moment of inertia times alpha. Correct. It's going to be moment of inertia times alpha. Correct. Perfect. And then We can go to moment of inertia because this is a pulley. The pulley, we can take it as a disc or a cylinder, and the moment of inertia is the same for both, right? So moment of inertia for pulley is equals to 1/2, and we call it right here m3 times r squared. Usually we use this r, right? This big R because it's gonna be constant. Okay, this R square. Okay, perfect. The same thing we can do right here, right? Big R. And also we know that alpha is related to acceleration, correct? Alpha is acceleration divided by R. When we substitute this value, what do we have? Let me do right here. It's gonna be 1/2 m3 times R square times a divided by R. This is also the big R right here, right? Big R, right? Big R. So conclusion from here, we can see as you can see, R is cancelled, and we have T2 minus T1 is equals to 1/2 m3a. R is cancelled. Okay, great. Now let's combine these quantities. Let's combine them and let's solve for acceleration. Let's do it. Let's do it. Look, what do we have right here? We have T1 is given, and T2, we can substitute from here, right? T2 is equals to m2g minus m2a. Correct? Well, what do we have right here then? We have that this is equals to m2g minus m2a, correct? This is equals to, no, not yet, minus T1, what is T1? T1 is minus m1a, correct? This is equals to 1/2 m3a. When we rearrange all of this, what do we have? We have m2g is equals to m1 plus m2 plus 1/2 m3, correct, times the acceleration. Correct. From here we can find acceleration. Let me put it right here. Okay, acceleration then is equals to m2g over m1 plus m2 plus 1/2 m3. That should be the acceleration. What about T1? Okay, where? Oh my God, T1. Let me do it right here. So T1 is equals to m1 times acceleration. So it's equals actually to m1 m2 divided by m1 plus m2 plus 1/2 m3 times acceleration. No, times g, right? Times g, because acceleration is this. Okay, times g. Perfect. What about T2? T2 is equals to, let's go to this one right here. T2 is equals to 1/2 m3 times acceleration plus T1. And what is this? Well, this is gonna be m1 plus 1/2 m3, correct, times m2 g divided by this quantity, m1 plus m2 plus 1/2 m3. Correct? Perfect. Let's try to use now angular momentum to find acceleration. Let's try to find this acceleration. Okay, let's do it. It's the same problem, correct? It's the same problem, but now let's use angular momentum. Let's use angular momentum. Okay, now angular momentum, the torque angular momentum for this system is equals to m1 v1, correct, or r sine theta, let's say theta 1 plus what? Plus m2, let's go to this one, m2 v2 r sine theta 2. All right, where's this idea? Okay, if we have this pulley right here, so we have this is the line of action, correct? We have now the particle moving with some velocity. This is m, some velocity. Also we have this is m1, this is m2, correct? Also with some velocity 2. This is 1. Right, at the end these two are the same, right? v1 and v2 the same velocities, correct? And this is the perpendicular distance of r perpendicular, correct? Perfect. And what is the angle? Look, this is, we can use also r is a big r, right? The radius, correct? And oh, it's the same as perpendicular. But what is the angle? 90 degrees. So sine, these two have right angle 90 degrees. So this is 90 degrees, 90 degrees. Sine 90 degrees is 1. Plus what? Also plus, this is the angular momentum, right? For these two object. What about the momentum for the pulley? Well, gonna be, according to this, gonna be angular what should be angular momentum? Gonna be moment of inertia times omega. Correct. Perfect. Now let's do it. The velocity again are the same. So this is equals to 2m1v times r plus m2v times r plus moment of inertia times omega. Right? Because right here we have a torque. Right? What is a torque produced in this case? Torque is equals to in this case is equals to r perpendicular, correct, times the force. What is the force acting? We have a pulley. The force acting is gonna be m2 times g. Right? It's the force that is making the rotation, the torque, right? Perfect. So then this is equals to r times m2g. Also, we can apply this definition for torque, right? Tau is equals to the derivative of angular momentum. This is angular momentum, correct? Respect to time. So this is equals to the derivative of this amount, m1 v r plus m2 v r, correct, plus moment of inertia times omega. Perfect. This is respect to time, right? Respect to time. And what is this? This is gonna be this is constant, correct? It's constant, but the velocity is changing, right? Being accelerating, correct? So what do we have? This is m1 times r times acceleration, correct? Plus m2 times r, one more time, this is constant, right? Times r times acceleration, plus moment of inertia times alpha. Remember the derivative of omega with respect to time is equals to alpha, and the derivative of v with respect to time, what is acceleration. Correct? Perfect. And what should be, let's go back, let's go and continue. So what do we have? This is equals to m1 plus m2 times r acceleration plus, again, what is the moment of inertia for this disc or cylinder? 1/2 mr squared. And what should be alpha? Is equals to acceleration divided by r. Correct? And let's substitute this value right here. It's gonna be r m2 times g, torque. You can see r is cancelled. And what do we have? We have that m2g is equals to what? This is m3, correct? This is m3. So it's equals to m1 plus m2 plus 1/2 m3 times acceleration. When we solve for acceleration, we get the same answer as before. Correct? So using in this way the momentum, we get the same answer as if we use only forces when we're dealing with torques. Correct? Perfect. And with this, we finish this chapter. It's gonna be rotational dynamics, part 1. Part 2 is angular momentum. Okay, thank you. See you in the next chapter. Bye.